All right, for this lesson, we're going to take a look at, with our angles and standard rotation, what our trig ratios would be and how they would fit into this concept. So the first part is we need to figure out how to create, based on the points or based on the rotation, what my right angle triangle would be. Because remember, all of our trig ratios are based on those right angle triangles. One concept we need to know for that is the Pythagorean theorem, where the hypotenuse squared is equal to the two legs squared and added together. But in trig, we use x, y, and r instead of a, b, and c, because we're doing all this on a grid. And we can see in the picture here, we have one leg is going to be our x value. We have one leg is going to be our y value, all connecting to a point here. And then because this could theoretically go all the way around in a radius, instead of saying our hypotenuse, we call it just that, r, for our radius. We're going to have the point P, which is our x and our y value, on the terminal arm. And the distance between the points is our radius formed by the rotation. If we put this into practice, it says, with example 1, sketch the rotation angle in standard position and calculate the exact distance from the origin to a given point. Where appropriate, write the answer in simplest mixed radical form. We're going to start to see that more and more of these are going to wind up being radicals, because typically we don't have nice round numbers for all the side lengths of a right angle triangle. So we're going to draw our y-axis, we're going to draw our x-axis, we're going to find our point, in this case, -5 and 12. We have our rotation angle, would exist here. And then we're going to show our reference angle by drawing a dotted line straight down to the x-axis. So based on this point, I know that we're going to have a length here of 5. We're going to have a length here of 12, because from my point, that's my x and y values. And I'm solving for my r value. So I can say that r squared is equal to 5 squared plus 12 squared, or my x squared plus my y squared. R squared is going to equal 25 plus 144, or 169. And then when I take the square root of that, r is equal to square root of 169, or just 13. So I have this right angle here where I have the side lengths of 12, 5, and 13. I'm going to go on to my next example. There's my y. There's my x. I have the point of -2 and 6. Sorry, -2 and -6. So here's point Q down there. There's my rotation angle. And once again, I'm going to draw a dotted line that connects it right back to the x-axis, knowing that I'm solving for my r once again, but I know that my x value is going to be 2, and my y value is going to be 6. Even though they're negative, remembering that the lengths are the sides of a two-dimensional shape, we always consider positive. So my r squared is going to equal 2 squared plus 6 squared, or r squared is going to equal 4 plus 36, which is going to be 40. R is going to equal the square root of 40, but 40 isn't a perfect square, so all I can do is simplify the radical to 2 root 10. How does this apply to our trig ratios? Well, we remember that our trig ratios are based on our angle that we're looking at inside of a right angle triangle, where I have my side opposite, I have my side adjacent to or beside, and then the longest side will always be my hypotenuse. So if I'm following the SOHCAHTOA, sine is equal to my opposite over my hypotenuse. Cos is equal to my adjacent over hypotenuse. And tan is equal to my opposite over my adjacent. How does that translate to the shapes that we have here? Well, the right angle we create is always going to have that acute angle is our reference angle. That's why we always draw it straight to the x-axis, which means that the side length that is opposite is always going to be y. The side length that's adjacent to is always going to be x. And the longest side length is always going to be r. So I can say now that sine of the angle is going to be my y over my r, cos is my x over my r, and tan is my y over my x. And like in the previous examples that we already did up here, that's a reason why we need to solve for what our r value is. We need to know what all three side lengths of these triangles are to be able to state what those ratios are. So, if it gives us an example where I have the point 15 and 8 lies on the terminal arm, I know that the first coordinate represents my x, the second coordinate represents my y, and I still, like we did in the previous examples, have to solve for my r. So r squared is going to equal 15 squared plus 8 squared. Well, 15 squared plus 8 squared is going to be 289. And r is going to equal the square root of 289, which is actually a perfect square. It's just going to be 17. From there, I can state what my trig ratios are. I know that sine of my angle is equal to y over r, which in this case is 8 over 17. I know that cos of my angle is x over r, which is 15 over 17. And I know that tan of my angle is going to be the same as y over x, which is going to be 8 over 15. And then I would just double check to see if I could reduce any of these fractions, which in all these cases, I can't. It just doesn't work.